Picking up where we left off in the last video here, we're going to look at an example. We have the differential equation 2x y double prime plus 5y prime plus xy equals 0. And because x is a factor in the term that contains y double prime, x equals 0 is a singular point. And because the exponent on x appears, it's 1, it's 2 or less, that makes x equals 0 a regular singular point. For our purposes, that means we know that our form of solution is going to be y equals the sum as n goes from 0 to infinity of c sub n x to the n plus r. That plus r is different from the previous set of videos, and that plus r exists because x equals 0 does zero out the y double prime term. Right now I don't want to look at the rest of the directions. We'll look at them later, but I just want to show you what the method of Frobenius looks like. We start with that y equals the sum as n goes from 0 to infinity of c sub n x to the n plus r. And that gives us a derivative, y prime is equal to a sum of n plus r c sub n x to the n plus r minus 1. I said in a previous video, r can be an integer, but it can also be a rational number. In fact, it can be any kind of number. We'll only see integer and rational numbers. The point here is, if r is, say, 1/2, then the power series would look like c sub 0 square root of x plus c sub 1x to the 3/2 and so on. And when we differentiate this, the first term does not differentiate to 0. That was characteristic in the last set of videos, and that is what made it so that our index changed when we differentiated. Here, with this n plus r exponent, the index doesn't change when we differentiate. So I'd say the two things that make this process different from the previous set of videos is the existence of the plus r in the exponent and the fact that when we differentiate, the starting value for the index does not change, at least not with this method. That also gives us a y double prime, which is the sum, again, as n goes from 0 to infinity, of n plus r times n plus r minus 1, c sub n x to the n plus r minus 2. Yeah, I fit that in. All right, now we're going to plug everything in here. So we've got the, for y double prime, we've got that sum as n goes from 0 to infinity. There's this 2x, so I'm going to put that 2 inside the sigma. The x is going to increase the exponent on x by 1. So inside the sigma, our expression is n plus r minus 1, c sub n x to the n plus r minus 1. Next term, plus 5y prime, is going to give us the sum as n goes from 0 to infinity of 5 n plus r c sub n x to the n plus r minus 1. And then for the xy term, x is again going to multiply by x to the n plus r, and that exponent is going to be a little bigger, right? So I'm going to go to the next line here. Plus the sum as n goes from 0 to infinity of c sub n x to the n plus r plus 1. And all of that is equal to 0. Remember, we're maintaining the structure of an equation. Looking at the exponents that we have in our sigma expressions, we have two instances of n plus r minus 1 in the exponent and one of n plus r plus 1. If we were to take the n plus r minus 1 exponent and add 2 to that to make it match the n plus r plus 1, then to offset that, I would need to decrease the starting value for the index. N would go from 0 to, I'd write down k equals -2, and I'm going to avoid a negative starting value for the index. So instead of changing the n plus r minus 1, I'm going to change the n plus r plus 1. And all of the exponents are going to become k plus r minus 1. I noticed that the first two sigma expressions start at n equals 0, and they both have x to the n plus r minus 1. So we can actually go ahead and combine those right now. So I'm going to do that. So we've got the sum as k goes from 0 to infinity, and from the first sigma expression, we're going to have 2 times k plus r times k plus r minus 1. And from the second sigma expression, we're going to pick up a 5 times k plus r. Both of those sigma expressions have factors of c sub k x to the k plus r minus 1 once we transfer or translate, I guess, substitute that exponent. And then for the third sigma expression, we're going to actually make the change to the exponent. And the result of that is going to be the sum as k goes from 2 to infinity of c sub k minus 2 x to the k plus r minus 1 equals 0, because we're subtracting 2 from each of those expressions, or making it look like we're subtracting 2, and then offsetting by increasing the starting value of the index. Now I'm going to write down a little note to myself. This is kind of like algebraic bookkeeping here. Inside the first sigma expression here, inside the brackets, we've got k plus r as a factor in both terms, so I'm going to factor that out. And then I'm going to distribute the 2 into the k plus r minus 1, and we have 2k plus 2r minus 2. And then having factored k plus r from the second term, we also have a plus 5 in there. And that's going to give us k plus r and then 2k plus 2r plus 3. Something like that can just make a sigma expression like this a little bit easier to work with, and will probably help with our recurrence relation later. For now, we've got two sigma expressions. One of them is the sum as k goes from 0 to infinity of that k plus r times the quantity of 2k plus 2r plus 3 c sub k x to the k plus r minus 1, plus the other one, the sum as k goes from 2 to infinity c sub k minus 2 x to the k plus r minus 1. Because these indices don't match, we need to make that happen. And so we're going to write down the first two terms of the first sigma expression. For the k equals 0 term, we have r times the quantity of 2r plus 3, c sub 0, and then that would be x to the r minus 1. For the k equals 1 term, we'll then add r plus 1 times the quantity of 2r plus 5, c sub 1, x to the k plus r. Because we know where we're going, we can go ahead and set this equal to 0. And I realize that second exponent shouldn't have been k plus r, it should simply be r. This gives us two equations, right? Because we know the term on the right-hand side for x to the r minus 1 is 0, and for x to the r is also 0. So we have that r times 2r plus 3 c sub 0 is equal to 0, and we have that r plus 1 times 2r plus 5 c sub 1 is equal to 0. What I'm about to tell you is going to seem a little bit like making stuff up, but I'll touch on it as we go. The term that has the smallest exponent is the one that we're going to use to find the value of r. So we've got this r times 2r plus 3 times c naught is equal to 0. There's going to be nothing to be gained by saying, what if c naught is the thing that's 0? So we're never going to make that assumption. The assumption we're going to make is that r times 2r plus 3 is equal to 0, and that's what we're going to use actually to find the values of r. Solving this, we get that r is equal to 0 or negative 3 halves. For a second order differential equation, we're never going to have more than two values for r, so we take that, we're going to run with it later. For now, I want to call your attention to the other equation that we have. If we were to take 2r plus 1, 2r plus 5, c1 equals 0, and make all the same choices, that is to say, well, c1 isn't going to be 0, so then r is negative 1 or negative 5 halves, then what we have is too many r's. And it'll turn out those r's won't work. They don't give us a solution that's viable. As a result, we use the second equation here to inform that c1 is going to equal 0. A short version of why the first one gives us r values and not the second one is that if the indices that we had, k equals 0 and k equals 2, only differed by 1, we would never have that second equation involving c1. We will always have one involving c sub 0. For further motivation, I'll just say this is what Frobenius told us, and I trust him, so we're rolling with it. Now, looking at the rest of the expression that we have here, we have written down the k equals 0 and k equals 1 terms for the first sigma expression, and now we are ready to combine all of this into a single sigma expression. We will then have the sum as k goes from 2 to infinity of this k plus r, 2k plus 2r plus 3 times c sub k plus c sub k minus 2, all that times x to the k plus r minus 1 is equal to 0. As before, we're going to solve for the constant that has the largest subscript. So here we have c sub k is equal to negative 1 over the quantity of k plus r times the quantity of 2k plus 2r plus 3 times c sub k minus 2. And I'm going to note that k starts at 2, goes to 3, 4, etc. From this, we're going to get two recurrence relations. One of them is going to come from r equals 0, and the other is going to come from r equals negative 3 halves. For r equals 0, we have c sub k is equal to negative 1 over k times the quantity of 2k plus 3, c sub k minus 2. And for r equals negative 3 halves, we have c sub k is equal to negative 1 over k minus 3 halves times 2k when all is said and done times c sub k minus 2. Rather than leaving that second denominator the way it is, it's got a fraction in it, but 2k has a factor of 2 that I can use to distribute in there. So I'm going to rewrite this as c sub k is equal to negative 1 over the quantity of 2k minus 3 times k c sub k minus 2. So you see we have two recurrence relations, one for each value of r. I want to talk about that r again for just a moment here. If we back up a little bit, we had this equation r times the quantity of 2r plus 3 is equal to 0. This is called an indicial equation. And its solutions, or its roots, are called the indicial roots. Backing up even further to the instructions here, we were told to show that the indicial roots do not differ by an integer. And we have here r equals 0 and r equals negative 3 halves, and they do not differ by an integer. When we subtract them, we don't get an integer. That's a distinction that is going to be important later. In particular, it'll be important when they do differ by an integer. We'll get to that later, but I wanted to flag the vocabulary indicial equation and indicial roots. And also, I'll remind you, the indicial equation comes from the term that has the smallest exponent on x. Now we're going to use our recurrence relations. I didn't write down here, but I will now, that k, actually I'll put it up here. K starts at 2, goes to 3, 4, etc. And this is going to allow us to generate our constants here, right? So for k equals 2 for the first recurrence relation, we have c sub 2 is equal to negative 1 over 2 times 7 c sub 0. For k equals 3, we have c sub 3 is equal to, I don't really care what it is because it's times c1, and somewhere along the line here we decided that c1 was 0, so we don't need to write that one down. K equals 4, we've got c sub 4 is equal to, after all is said and done, negative 1 over 44 c sub 2, which then becomes 1 over 616 c sub 0, and I'm going to call that good enough for that set of constants. Using the second recurrence relation, when k equals 2, we get c sub 2 is equal to negative 1/2 c sub 0. C sub 3 again depends on c sub 1, but c sub 1 is 0. And c sub 4 is negative 1 over 20 c sub 2, giving us 1 over 40 times c sub 0. Ordinarily at this point, we might write down that y is equal to, from the first series, we have c sub 0 times the quantity of 1 minus 1/14 x squared plus 1 over 616 x to the 4th plus dot dot dot. As a reminder, remember our solutions look like c0 plus c1x plus c2x squared and so on. So when I factor out a c0, I'm left with 1, but we decided c1 was equal to 0. Now we have plus for the second series. We're going to write down c sub 0 times the quantity of 1 minus 1 half x squared plus 1 over 40 x to the fourth plus dot dot dot. Except we've made a couple of mistakes here. Number 1, there's nothing to tell us that C0 for the first series should be the same as C0 for the second series. And so in the first series, what I'm going to do is I'm going to take uppercase C1 and let it replace C sub 0. For the second series, I'm going to take uppercase C2 and let it replace C sub 0. And what we're doing is we're just parsing out the two constants for the two different solutions that we found. That was one mistake that we made. The other mistake is that our solution has as its general term not an x to the n, but an x to the n plus r. Now that doesn't make any difference when r was equal to 0, but it does make a difference when r was equal to negative 3 halves. So we need to, in the second series, we need to augment that solution with an x to the negative 3 halves. And I'm going to refer to this as like, this is the Frobenius thing. Y equals C1 times the first series that we got, plus C2 times x to the negative 3 halves times the second series that we got, forms our general solution. Our two independent solutions are y1 equals 1 minus 1/14 x squared plus 1 over 6/16 x to the fourth plus dot dot dot. And then y2 is equal to this x to the negative 3 halves times 1 minus 1 half x squared plus 1 over 40 x to the fourth plus our dot dot dot. I'd leave it like this, leave that x to the negative 3 halves hanging out there. And this is the method of Frobenius.